Hello, my name's Songwei, and welcome back to another Java video. Today we're going to be talking about trees. So far, we've talked about linear sequential data structures like arrays, ArrayList, linked, and linked lists. Trees are a hierarchical data structure, which means that there are kind of different levels to it rather than just being linked more linearly. So what is a tree? Well, like I said before, it's a hierarchical recursive data structure. So by a recursive data structure, what I mean is that a lot of the functions inside and a lot of the methods inside use recursion. So for example, a tree is made up of a left subtree, a root node, and then a right subtree, and then each individual subtree has another subtree, a node, and then another subtree. And so in that way, it's recursive. So trees have nodes, which are individual entities that represent objects, and those are connected by edges or links, which represent the way that nodes are related. So these go in one direction, and it's easy for a program to get from one node to another if there are different edges connecting them. The root node is the node at the very top of a tree, which is the node that the tree starts out from. The parent node is every single node except for the node that just has one edge running upward to another node, and the child node is the two subtrees of that parent node. We also have leaf nodes, which is the node at the very bottommost layer of the tree without any child nodes. So this is an image of what a tree can look like. It can have many different paths to many different children, and it can end at any place it wants. But today we're going to be focusing on a very specific type of tree called a binary search tree, which we'll be abbreviating as BST. So what is a binary search tree? Where a binary search tree has a kind of way of ordering. So everything to the left is smaller than the root node, and everything to the right is larger than the root node, and that follows for all of the other nodes. So for example, if we have a list of numbers 25, 10, 22, 6, 4, and 35, and we want to put it into a binary search tree, then we would start out by putting 25, and then we would look at the next number, which is 10, and since that's smaller than 25, it would go in the left. Since for this one, we'll do that everything to the left is smaller and everything to the right is larger. And then we look at the next node, which is 22. So 22 is smaller than 25, which means it goes to the left subtree, but it's larger than 10, which means it goes to the right subtree of 10. And then we look at 6, which is the next number. 6 is smaller than 25, smaller than 10, which means it goes to the next smaller subtree there. And then we have 4. So we start from the root node again, so smaller than 25, smaller than 10, smaller than 6, which means 4 goes here. And then we have 35. 35 is larger than 25, which means it goes to the right. And that's how we would create the binary search tree. So now let's go over a couple of different traversals. So there are two main types of traversals. There's breadth first traversal, which means going from left to right first, and there's also depth first traversal, which is going up and down rather than left to right. So in depth first, there are three different types. There's pre-order, in-order, and post-order traversal. So pre-order traversal is when you go to pre-order traversal is when you go to the root node first, and then the left subtree and the right subtree. In-order traversal is you go to the left node, then the root node, then the right, and post-order is you go to the left, right, and then the root node. So for example, if we were to do pre-order traversal on this tree, then we would go to the root node first, which is 25, and then we go to the left subtree, And then in the left subtree, we have to do pre-order traversal again, so we'd go to 10, and then we go to the left subtree again, so that's 6, go to the left subtree again, so that's 4, and then we come back and we go to the right subtree, which is 22, and then go back to the right subtree of 25, which is 35. If we were to do in order, then we would want to go to the left subtree, then the root node, then the right subtree. So we go to the left subtree, but this also has another left subtree, which means we need to go all the way down to 4. Then we go to 6. Then we go to 10, since that's the root node. Then we go back to its right subtree. Then remember, this is recursive, and so we had the 25 at the start. So we go back to the 25, then we go to the 35. So to look at a little more tree terminology, we have depth and height. So the depth starts from the very top. So the root has a depth of 0, and the depth of this 10 node and 35 would each be 1. And we also have height. So height goes from bottom up. So the height of 4, which is this leaf node, would be 0, and the height of 6 would be 1. And binary trees can have at most 2 children. So unlike this tree, which can have many different children, this binary tree only has 2 children, and in this case it follows a specific method of the left one being smaller and the right one being larger. Also, different types of binary trees. So first we have the perfect binary tree, and this is where every single leaf is on the same level and every non-leaf has exactly 2 children. So it's kind of what you would imagine a quote-unquote perfect tree would look like, with every single node having 2 children and all of the leaf nodes ending at the same level. Then we have a full binary tree, which is where just every non-leaf node has 2 children. So all of the leaf nodes don't necessarily have to be on the same level, they just all need to have 2 children. And finally, we have a complete binary tree, which is a tree that is nearly perfect or is perfect, and this is basically a perfect tree except from the last level, so at the very bottom, to the second to last level, where there can still be some inconsistencies. So where can we use binary trees? Where we can use these for evaluating expressions, even for sorts of game theory, like figuring out the best decisions to make in tic-tac-toe, or chess, or other games like that. So let's take a look at how to code a tree. So we start out with a class called treeNode, which has the value in the node, and it has its right node and its left node. And these are all tree nodes, so it's the individual node that holds one value. So let's pretend that we already have the constructors and the getters and setters, and we're going to look at how to write traversals. So first, let's write the in-order traversal method, and remember this is when you go from the node's left subtree, then to the node, then to the right subtree. We always need to check whether the tree node is null, because if the tree node is null, that means you can't traverse it because nothing exists. So we want to start out with making sure it's not null. And then we want to go to the left. So this is recursive, which means we can continue calling in order on this tree's left node, which we can do with a getLeft method, which is one of the getters that we would have typed before. And then we can get the root node. So this get value is the value in the root node, or the current node that you're in right now. And then you can call in order on the right subtree, and this will repeat itself. if you have the tree node and then you go into in order, then you would call the same method on get left, which means it goes back here and then it checks whether it's null or not, and then it goes to its left again, and once it's gone all the way down to the very bottom, then it starts doing get value and printing out the root node, and then once it's done with that, then it goes to the right subtree and starts printing out values there. So that was a very basic introduction to trees. I hope you learned something, and I'll see you next time. Bye!